don't know. Can you hear me well? We're gonna have a mic test before.
Yes, yes, I can. Yeah.
Okay, good. Hello. I'm here.
Hello, can you hear me?
Yes, I can hear you.
Cool.
We can also hear some background noise from the XY, I think.
Yeah, because the microphone was enabled.
Hello, everyone.
Hey. Well, yeah, I thought because there is like a smaller group here, I thought maybe I'm just gonna enable the mic function so that you could ask questions straight away to Michał. I'm gonna do the announcements and disclaimers maybe once we have a few more people. Yeah, but I have a few things to say for the beginning, for the starters.
Sounds good. Let's give it a minute or two.
I would say let's wait maybe one more minute, one or two more minutes, and I'll start, and then I'll hand over the voice to Michał.
Sure. I'm trying to figure the presenter view with. Okay, never mind. Let's do it this way.
I think when you clicked the slideshow, we could see the slides.
Sure, yeah, but I can see the speaker view. Sorry.
Okay,
speaker
okay.
notes.
The speaker notes. Okay, that's fine.
Okay, never mind. Oh, wait.
Okay, I think
okay. Trying to hide the tab on the top, but I think it's the best I can do.
I think this is fine. I really think this is fine.
Cool.
Okay, let me start then. And well, so first thing is that this call is being recorded so that we can upload this to our YouTube channel. Second thing is, well, this call is like a reoccurring monthly event. The last time Michał gave us an intro and overview of the new engine, and that is available on our YouTube channel if someone wants to, take a look. And today, this is gonna be rather an update, so there will be no going on a high level what's the new execution engine. It's rather gonna be what's changed and what's new, and this is what Michał is gonna present today. Yeah, and I let the chat available, not to use this Q&A eventually. The mics are also, I mean, you can also unmute yourself. I think sometime in a few months before or last year when we were doing kind of the similar thing, we were allowing microphones so that, you could chat with Michał and ask questions straight away. So let's try this format this time. And I think that being said, this is all I wanted to say. And yeah, I think, Michał, you could start.
Sure. So I will give some updates on the new execution engine, and also by a request from the community, I also want to talk about some benchmarking and something that I was working on for a very long time, but finally came to conclusion and it's implemented for 2.0. I think it might be interesting technical topic, and yeah, so let's start with the update. Do you guys see my changing slides? There's some issue. One second.
We only see the, well, now we don't see anything.
Yes.
Cover of the slide.
One sec. I will just forget about speaker notes and one second. Link. Okay, that's better. Oh, sure. So the update and the benchmark and Q&A. So that's the agenda for today. VM2 update. So we can focus with past RCs being resolved. I can also focus I can focus more time on the new VM. Basically, I also have Igor that is also contributing to the new VM. With the sprint, we just merged today some improved cost function, cost accounting. So we are moving forward, moving towards a functional VM with costs properly implemented, and like fixing, basically cleaning up some mess along the way. And yeah, so that was from Igor. That was very important because like lack of proper accounting is also hard to call this like shippable product where we don't properly account for things, right? So we implemented the sprint, and from my side, I took a bigger bigger task, which is implementing basically porting 2.0 messages API into the new VM. I wanted it to be really the messages. I wanted it to be really like first-class citizen in the smart contract development. That means the messages should be easily defined. You should be able to easily define messages for your contract. You should be able to emit them and really think about them in terms of like this is important, right? Like I really want to emit some events, and I need to have, as a developer, I need to have right tools for that. And yeah, so along the way, we will try to move forward with new features. I mean, not really new, but at least like retrofitting 2.0 features into a new VM, cleanups, refactoring, and basically making improvements while we do also new stuff. And that's how it looks like. That's how it looks like. That was my intention, to be very high level, right? And no surprise there. It's not also something different from other high level SDKs for blockchains. So on the right top, you can see the definition of a transfer event. And on the left side, you can see it's part of the schema. At the bottom, you have list of messages that are defined for your contract, the name and the declaration. And the declaration, as you can see at the top of that snippet, it is the description of the type, basically. So on the left side, you can see how can you, if you consume the schema, it tells, as a consumer of the schema, it will tell you how to deserialize given type. Like, so if you, let's say, wait for SSE, if you wait for SSE events, you can, and you have schema, you can deserialize the payload of the message. So that should be sufficient for a consumer.
Michał, we're losing you. I think you're
Oh,
on
no,
mute
it's,
now.
yeah, I had a guess. I had to close the doors. 1 second. Yeah.
Okay.
So on the right side, this is the API where it's copied from the CP18 example contract from the new VM. So basically, the emit message function, you give it an instance of an object, and then it goes into the execution result, and then after it is executed, it will be part of it will be pushed into the SSE, just like in 2.0, right? The only difference, it is the same implementation. The only small detail is that 2.0 required message topics to be registered upfront. But in this implementation, I decided to make the registration lazy. So upon first emit of a given message, it will be registered. It is a minor detail. It's pending review, of course, but I think it makes it easier for people to reason about. Even so that means even if it's not registered or even if it's not used, it will be still reflected in the schema. So yeah. In my opinion, it should improve the user experience for developers. I change. Yeah, so we do have CP78 board. It's me and Igor. We think it's just a test contract, like a proof of concept. I would say, like proving that new VM SDK and API and the VM and all of that is sufficient to write a serious contract, but that also means we will have to use the messages API in the new VM to see if that makes sense, right? If that API is sufficient for porting into a real contract. I do believe it is. It is very simple, as you can see. It's just one function with most of the work is done under the hood. But we'll see. For now, it's in CP18. It will be part of a PR. I did most of the work. I was waiting for Igor's PR to match with the host function calls because he wired up some train spec details. So I'm rebasing on his work. I think it should be probably tomorrow. I should be done with the PR, which implements this with all the costing and limits and just like in 2.0. Okay, I think that's the last slide from the update. We could move all the questions at the end, if that makes sense.
Yeah, let's do that. We have a Q&A session at the end.
Cool. Yeah, it's just 30 minutes for all. So I will try to be quick with this. So by a request from the community, some discussion or some update on the benchmarking. So and testing. I choose this topic because it is something that was like I started research on this long before I moved to association. I think back in the labs, I started to also tweak and research this. And there was a couple of iterations. I will try to describe each iteration we had and the methodology. So what is it about? So basically, I want to talk about like my latest work on the gas accounting, aka the cycle-based gas accounting, and how I started with this and how I end up like what were the steps along the way. So what was the objective? The objective of the gas accounting was to assign fair, predictable gas costs to WASM opcodes. Sounds simple, right? But it turns. I mean, in retrospective, it sounds simple to me also. But in the beginning, it was just unknown, basically. Like, how do you get from opcode, which has some time to like it executes in it takes some amount of time to execute, and then how to make a gas out of it, right? So the purpose of that was to basically computationally expensive opcodes are costed appropriately. So you can see, let's say, yeah, so you can imagine, let's say, addition or subtraction, or let's say bit operations are very like least computationally expensive, right? But let's say calling other functions or looping or floating points are much more expensive, especially in the interpreter, which we use in 2.0. But we will not use interpreter in 2.1, right, with the new VM. And we need to appropriately compute the gas costs for each of the opcodes. And there's many challenges with that. You have to assign gas, you have to set a time limit for execution, and you have max gas per block, and we also have in 2.0 WASM lanes and many other limits, right? So how do you navigate in this complex area? And also, as a last point here, this is something that took me really long time to like figure it out. Basically, the might not be surprised to some people, but the WASM you give us, it's not the same WASM as we execute. That means for each WASM, we inject gas costs, which modifies the bytecode. So it's already not the same, right? And we also do modification for deterministic stack height for WASM, which makes it very similar to x86 executables, where you have like fixed size of stack for calling functions. So it takes non-trivial amount of overhead to your WASM, basically. And it's not really predictable. It's not very, like, deterministic. In the end, turns out some opcodes were less prone to the overhead. Some opcodes were more prone to the overhead. Let's say basic arithmetic wasn't that. The measurement of overhead of basic arithmetic wasn't so high compared to, let's say, call, where calling a function, like, at least there is some trampoline and then some overhead, some gas, some stack height counter. So some computation is more expensive than others, right? But you have to really measure that and reflect that. So the original concept, even before this, just realized when I was preparing for this session, just even before, like, or the OG Casper mainnet, we basically cargo culted opcode codes from, I don't remember, I think it was early days of Polkadot maybe, or I wasn't there even. So we just had some gas costs per opcode that we thought are fine, and we basically inherited that, right? So that was our first iteration. At some point, there was another iteration where we were worried about slow WASMs, which let me, I already spent some time on researching this, but in the interim, I made some benchmark and some kind of brute force algorithm to ensure that the slow WASM were costed appropriately to secure the network. But that wasn't really fair. But it was a solution for a problem, but it wasn't really fair, right? So that were like 2 iterations already. But this original concept is a first step towards like fair accounting. So how do you measure gas for opcode? You need measure time. You have to measure time, and you need to measure it for some reference hardware, right? All validators have different CPU architectures, different OS. Maybe most, I would say, I can't say for sure, right? But I would say maybe 99.9% it's Linux, probably LTS, whatever, right? Most likely not Linux, not macOS. So that's already some idea what should be the reference hardware. I used my old desktop for measurements. It was Ryzen 3950, if I remember correctly. It's not old, not new, but kind of performant enough. I would say that is maybe within some maybe more, maybe better than average. I would say from all the validators. So I think the hardware was fine. And then there's a first challenge. You have to implement extensive benchmark for all the opcodes. So you have to generate WASM for each opcode, and the WASM has to run many opcodes, and then you have to run the benchmark for each opcode, and you have to extract how it takes to execute just one opcode from, let's say, thousands of opcodes within the WASM. So then you have nanoseconds. So we have first variable, first data that out of this benchmark, right? That's very important. And then with some formula, you have to calculate that. I calling this like timeshare for each opcode. So you have two knobs. Let's imagine two knobs, like two limits. One is the block time, which is 16 seconds. At least at the time I was writing this, I chose 16 seconds, which was at the time the time spec value, and then target execution time. And the target execution time is the max gas per block. So you have two limits that you have to calculate the time into within those limits, right? So then you have the nanoseconds you multiply. So the timeshare is basically division of the timeshare per the nanoseconds of each opcode. So you have timeshare, which is a percentage of total computation space. Let's call that. And then once you have this timeshare, you can calculate that timeshare into the max gas per block. So basically what we have is a normalization of time into the abstract gas notion, right? So the result was, okay, we have gas cost normalized, so we do have some fair representation of gas cost per opcode. And let's say that there are some proofs. It's not formal proof, but more like kind of non-formal proof, and that I ran many more examples of that, many more different examples. And then it turns out, yeah, it is sound. On the idea, the approach was sound on paper, right? I imagine some kind of abstract architecture with 4 opcodes, some target limit, and that max gas. And then let's say you have opcode A, half a second, then you calculate timeshare, which is 25% of all the time. Like you can only execute 4 opcodes A, right? So that's like 25% of the time. And then multiply that by the target gas, and you get the gas basically. So we are recalculating the time into the gas. For each, you do it for each opcode, and then we do have example program, right? So just to verify, C and B, a program that executes C and B, you have sum of the gas is 100, which is within the limit. But when you recalculate, like when you go back from gas to time, then you see also it is within the time allocated, right? So it is matching the expectation, right? And there are some conclusions. Mainly, you can see how it is all moving. Like it's a different. You can have different observations that can also affect it. Something at that time, it was already some kind of like eureka moment for me, where you can see there is different values, let's say time limit, gas limit, opcode time, WASM, performance, and so on. And I drew some conclusions that you can increase the block time. If you increase the block time, then basically it will reduce the gas cost, because then basically it's a scaling issue where you extend the allowed gas limit, and then you basically you can pack more opcodes. We don't like, assuming you only change one variable, right? When you increase the gas per block, then also sorry, the first point was when you increase the block time, then it will reduce the gas cost per opcode, because it's a scaling, right? You have to fit more. If you have to fit more opcodes into the increased time, then it scales, right? When you increase the gas cost, then it's also increasing the gas cost per opcode, because it's also scaling, right? You have to scale the gas per opcode if you don't change the performance of the VM. So it's just a scaling, basically. And then another observation was at the time, okay, so when we decrease the time of execution per opcode, then it also decreases the gas cost per opcode, right? Because let's say if you have a VM1 is some kind of abstract VM1 is executing opcode A in half a second, if other VM executes the same opcode within, let's say, quarter of a second, then all the computation leads to smaller gas costs. And that was another interesting topic. That was also kind of another moment where I realized that Wasmer is a better choice, right? Because Wasmer is supposed to be faster, because the overhead. It's not a interpreter we will use in Wasmer. We will use ahead of time compiler, which is supposed to execute the code much faster without much overhead, right? I mean, there is overhead, right? But it's not the same as an interpreter we have. And then the measured gas costs were basically fixed values per opcode, some kind of value, right? That was first issue with this model, was that it was confusing, because we don't really think in terms of gas, right? Like, what is, like, okay, so the addition is, let's say, 100 gas, and what does that mean, right? It's just some abstract notion, right? Gas is some abstract notion still. At least that's the mental model of most people, including me, right? And there were some limitations as well of that benchmarking, that it was hard to really observe the overhead. So I was in this iteration, I was using just one run with all the overheads, I was benchmarking opcodes with gas counter, with deterministic stack height. So all the post processing was done for the WASM, but it was just that, right? I couldn't really see the difference between overhead and non-overhead. So that was also another thing that was confusing. Like, any change basically means we had to rerun the computation and just trust the values that were outputted in the benchmark, right? And oh yeah, so yes, so yeah, so refining the model, and then it wasn't huge change, but kind of makes sense. I guess you guys can also agree in later slides. Refining the model means that we will go for easier to understand model, like more intuitive, in my opinion, where this is the final step, right? So this cycle-based opcode gas accounting. So now, instead of doing like just one value, that one run of the benchmark or the overhead, and just trust this, I was digging much deeper into this topic, right, where I wanted to really make one run, but like extract some constant values from that benchmark run, right? Like, so turns out what we really want to do is go to the basics, look at the, let's say, CPU manual, and see how it is documented, and all the CPUs will give you, let's say, cycles. What is your operation? How much cycles it will, CPU cycles it will take. So that's what we want for our blockchain as well, right? We want to know how many cycles takes some WASM operation. But what is cycle anyway in a blockchain? Because we don't execute the same WASM as you give us. So we need to define the cycle. What is a cycle? So the first step was to define some smallest measurable operation as a baseline, and for interpret there's some prior art for this, and different VMs you choose different baselines. I saw, let's say, for ahead of time compiler, probably it doesn't make sense to use the same as in an interpreter. So for measuring the interpreter we have, I choose NOP as our smallest measurable operation. Why NOP? Because NOP captures, measuring the time for NOP captures the time the VM is instantiated, the time it takes to like increment the program counter and then do nothing, right? So this is the smallest operation. In my opinion, it is the smallest possible operation that can be measured. And that's important because later all the benchmark results for each opcode will be divided by that operation. So in other words, all the opcodes will be a multiplier of cycles per each opcode will be a multiplier of time it takes to execute smallest operation. So let's say NOP is, let's say, 1 second, just abstract 1 second, right? But let's say floating point addition is, let's say, 10 times the NOP. So then the cycle count for the floating point is basically 10, right? So we do have already definition of some cycles, and we know for each of the opcode the cycles might be different, right? And that's good because that's what we want. We want to have some kind of constant value, constant for each opcode. And then what's left is the Cascade multiplier, which is the variable part of the equation. So for each, that's where the benchmark really plays a huge role. And this is where we can also observe the difference between the the difference between non-overhead WASM benchmark and the benchmark with the overhead. So I have data sets somewhere. I think it's in my GitHub. I have the data set where I computed each opcode. I ran the benchmark. I computed each opcode cost, cycle, with overhead, without overhead, and then in the table I could see, okay, so call opcode without the overhead takes this amount of cycles, and then opcode call with the overhead is the multiplier is much higher because of the overhead, right? The gas counter and the stack height limiter increase the multiplier of the call opcode. And then, yeah, so we have to apply that for each opcode, and we could basically tweak, let's say, once we have some data already, like some kind of data set, we can still tweak this with some real WASM. Let's say slow WASMs. We can measure execution and then tweak the multipliers manually still. So then we don't operate blindly by changing some one value for each opcode, which is not intuitive, right? We can only work on the multiplier, and the multiplier is different, and we can really observe, let's say, if you look at the chain spec for 2.0, you can see arithmetic is the multiplier for arithmetic operations is mostly the same, but let's say call is much higher, let's say select or any other non-trivial operation has much higher overhead. And that overhead is the multiplier, the higher multiplier. And then, yeah, so then we can basically say in the cycles, in terms of cycles, we can validate that by a benchmark, by dividing the time by the smallest unit. And then the multiplier is derived by constantly running the benchmark without overhead and determining that given opcode is really much more expensive because of the processing we do. Advantages. So comparing to what we went with mainnet a long time ago with what we have now, it's really, we do have the coupling of the gas costs from the hardware, right? Because we use some specific hardware and we derive some cycles, we derive some multipliers, and like all the nodes have to agree with that. So if you have faster CPU in your node or slower, you have to it will be fine, right? Like maybe you will, if the block is saturated with deploys, maybe slower nodes could see that, but it's not dangerous. The consensus will be fine with that. But if you are faster, then it's even better, right? Because you will finish the computation, you will finish the execution faster than others. And so yeah, with multipliers can be adjusted. That's fine because we have benchmarks we can run, and then let's say we update the VM, we can rerun the benchmark, we can derive new multipliers, and it's all clear. Like we have some feedback loop we can run, and just I'm fine with the transparency. Basically, that this is clear. It's a relationship. We have cycles, right, derived from the benchmarks, and it's constant. It's even just literally hard-coded in the code that there is a cycle per opcode, and there is a multiplier, and that is in the change spec. And then this is also something we can take out of the benchmark. And summary. So yeah, like went from cargo-coded hard-coded gas cost, but didn't make sense really. That there were some values computed by a brute force algorithm that were safe but weren't fair. And then first we went with this just basic normalization, which I figured out in the beginning, and it was confused. And then we arrived at the cycle-based opcode cost accounting, which is, I think, looking at other chains, I think it's the de facto standard, I would say. As like looking at the prior art, there is some work on that in other chains as well, but not all. That was also surprising. Not all chains implement something like this. I won't point finger, but at least at the time I was researching this, there were some chains that didn't really figure this out yet. And this is the result of our so-called canary contract in the tests. So you can see expected, the red is the before 1.5x, green is 2.0 in the red. You can see it's within like 1-2% change increase for some entry points, but let's say set variables cost is about 40 to 35% cheaper, right, in the new model. And it's within like first, and third from the bottom, and fourth is, I would say, within the changes within noise, right? But this is the most rewarding change I saw, that this is 40% cheaper, and that was really rewarding for me. That I can see really positive impact, right? Like the model we run with 1.5x with this brute force algorithm was safe, right? But wasn't fair. And then when we incorporated fair code costs with cycles and multipliers, it really became fair, and that translated to cheaper execution. And that's not done yet because this model will be also ported to new VM, and that will hopefully, when I get to that, I would be able to also observe for similar workloads. I should be able to observe similar cost savings because of the basically cycles could be, if you really want to be pedantic about that, you can also say cycle per each opcode will be basically taken from the CPU manual, and then multiplier will be the one to match the cycle, the CPU cycle to a WASM cycle, right? Like WASM instruction. And next steps. Oh yeah, Adrian asked me why you have empty slide. So I thought there aren't really immediate next steps, I would say. Maybe based on the feedback on testnet or mainnet, we could make some tweaks, perhaps. Maybe improve the VM, like update interpreter in the interim. Maybe maybe I ran that idea by our economists, but maybe some kind of paper or something like that could be easier, just for like collaboration with other chains. That would be nice. Nice thing. What else? Like if I was mentioning being pedantic, but like if we really want to be pedantic about costs, we maybe don't want to. Maybe we could really define in the chain spec the saturation of execution. What I mean by that is define how much time of the block could be spent by computation. we do have WASM lanes, but it is gas based, right? But like we could say, if we can also benchmark all the native auction operations and all the transferring operations, then we can have cycles per each interaction with the chain. And then maybe in future, we could also like define the chain, like, okay, let's say 16-second block, maybe 16 seconds block is, let's say, I don't know, 1,000,000 cycles, right? And then let's say 30% of the cycles would be native operations, and then 70% of the cycles would be computation. And then we can also like be really precise about that. And then that's, yeah, I think in terms of like prior art, I think early days of WASM is like first attempt from Ethereum at moving to WASM bytecode. They defined that early in the process, that this amount of cycles is computation, this amount of cycles is something different, and they like, yeah, they started from that, right? Like, but in our case, it's kind of different because we started in different models, like, and we arrived at this. So, yeah. What else? Like, I don't know. Next steps is your feedback as well. if you agree, if you don't agree, I'm open to criticism, feedback, and discussion. Okay, Q&A. We ran out of time. I think, yeah, it's a short
Yes.
period of time.
I was thinking maybe for the next calls, I'm gonna make it a little bit longer because it's on a monthly basis.
Mhm.
It seems like half an hour is not enough.
Yeah, if you guys want more technical topics like this, maybe it's not enough, right? But
So we can definitely make it longer next time. I see
Helps.
we are over time, but I think if I hope everybody's fine to go another 5 minutes to answer any questions.
Sure.
So let's open the floor.
Yes. Everyone's, you can use your mics if you want to ask something or to share any feedback.
I would like to say something. Yeah, you were talking about benchmarking and just using your computer, your personal computer. Yeah, I would like to say that. I mean, you have a huge community of developers here that you could use if you need to. If you want to run on multiple machines, you just share the benchmark script, and everyone could run it, and then you'd have a distribution curve that would give you even better insight into your findings, I guess. Just
right. Yeah, that's a fair point. Yeah, we should something to consider. For now, we were more like just making a choice, basically. It wasn't deliberated, not including community. It was more like just making some choice, right? And yeah, we can revisit that in the future for sure. The code isn't public yet. It's very ugly and it's considered internal, but yeah, we can make some steps. Once we ship 2.0, maybe we can take some time to open source it and yeah, thank you.
Anyone else? Do you guys have any questions? Or maybe you have some ideas. What should we include in the next update? We're happy to hear that as well.
Yeah, I have some idea, but I would prefer to listen to the feedback from you guys, what you want to see more.
Yeah, come on, don't be shy.
I know this topic I choose is very dry, and but maybe next ones will be more friendly, not so dry.
It's fairly important one, right?
Oh, of course,
Yes.
it's very important. Like it is like foundation of the security, basically, making this right. But
Maybe
it's a non.
maybe as an idea, just throwing this out, some side-by-side comparison between the two execution engines with a contract that has been developed in both. And then we can look at both the code comparison as well as sort of gas and execution comparison between the.
Yep, sounds good.
Yeah, this sounds like a great idea to have like an actual example so that we can.
Right. Yeah, so we do have some example code, but yeah, that's
Well,
I
don't be
think
afraid.
one
Don't be afraid. I know how it goes to share ugly code and finished code, but you shouldn't be you shouldn't be shy. We're all
Sure.
the same here.
Sure. Yeah, so I just wanted to say that we do have example code. I think before the break, I did some comparison before, but I think we can with appropriate costs and stuff like we merged recently. Yeah, we could do more detailed comparison of code, especially
Yeah,
CP1878.
exactly. I would prepare sort of two, the same contract side by side in the two execution engines, and then literally run two, NCTL or some networks where we can, or I guess you can target it on the same network with a different VM, and just compare the execution.
Makes sense.
It's also a cool demonstration of the ability to target two different execution engines on the same network, just depending on the transaction configuration.
Right.
I'm generally not sure how useful it is to be so low level. You know, I mean, or to whom, which audience you're targeting with this course. I mean, generally, of course, this is interesting, but it's at least for me pretty hard to follow and to get some real, some real data where I just see like, okay, the new engine is, I don't know, 20% faster than the old one. Basically, what Michael said just now, to give some use some existing contracts and just see really, okay, what's the difference and what do I get? And I'm not interested, me personally, if one call is now, I don't know, 2 times faster than before, because maybe this call is used only in 2% of contracts, then yeah, you know what I mean?
Makes sense. Yeah. So,
I mean,
so what?
to respond to a little bit of that, I mean, this is not intended as sort of like a marketing call, right? Like it is low level for a reason, and the target audience therefore is people who are interested and or working with smart contracts and execution engines, and perhaps have experience doing so on other networks as well. And sort of dive more deeply into sort of the technical aspects of it. Whereas the information that you're sort of suggesting, like, hey, this is 20% faster than the old model, right? It falls more in that marketing bucket, and perhaps belongs in sort of different forums than this call. And I mean, I think that's why we're not seeing hundreds or thousands of people in this call like we see in like our X Spaces or other calls, right? So sort of self-selection in a way.
But I think we can find a sweet spot here and maybe like start the call with some high level, maybe like comparisons, and then dive deeper, and you know, some people can drop off at the time. Initially, when we were starting this series, last year it was a bi-weekly call, and there was people who were joining were mostly ODRA and grantees, so people who were building something on top of Casper. So maybe it was more targeted for this sort of audience. But I think that's no problem for us to do something like a few slides high level and then dive deeper.
Fair enough.
Sure.
Yeah, I think that makes a lot of sense. It's like you just see the results basically, and then you go much deeper and you see how it was accomplished.
Yeah,
absolutely, yes. All
Cool.
right,
Sounds good.
1 more minute for additional questions. Anyone? If not, I would just close the call, and the recording is going to be posted on our YouTube. So I'm going to also share in the groups the link to the recording for anyone who missed eventually. And because I don't see any questions in the chat, nobody is unmuting, so I guess that's it. Thank you very much, guys, and thank you very much, Michał, for the presentation, and speak to you on the next call.
Thank you, everyone, for joining.